Thank you very much for being here. Thanks the organizer, in particular to Paulo Castro for the very kind invitation. It's really a pleasure. Let me share my screen to hear the things I've learned with John just recently to optimize video. Oh, now it's asking something different. Oops.
You're sharing too much.
Oops.
You have to share only the presentation or only the PowerPoint window.
No, let me stop sharing.
Oh, you sort of close down that automated, yeah.
The thing that maybe I'm not going to share, optimize it, then it did something weird. Let me share here. Okay, let me see now. Is this okay now, Paulo? Can you
I think so.
Okay, good. So okay. Well, so let me release here my stopwatch.
I'm not sure.
No? Can you see my screen?
I think it's
I'm
okay.
seeing his slide.
Let me page it. Let's see if it works and let me know if anything goes wrong. So I'm going to be talking about wave-mediated Kuramoto-like synchronization. Let me start with something.
Your sound is too far away.
Yeah, can you turn your volume up a bit?
Let me turn my, it's maximum. Can you hear me now?
Yeah.
Okay, that's fine. Okay, let me hold it like this. So thank you. So let me show you this first slide. I'm going to show you as much as pictures and not much of the math modeling, just very quickly to, show you many things that the math model helps us to uncover. So this is a very simple example done many, many time ago that basically guided my intuition, acquired intuition to many simulations I'll do next. So we have this one cavity here on the top, the side view of the vessel, the shaking with the shaking frequency. Usually I use it 80 Hertz in the numerics. And here on the bottom, we see the droplet at the left of the cavity with this shallow region on the sides where the droplet does not like to walk. And we see that the wave-mediated dynamics brings the droplet to the middle of the cavity, and it oscillates like a harmonic oscillator as a first approximation. And we see the wave pattern. This is in time. Okay, this is a 1D simulation. All my simulations today are 1D, one-dimensional. It's a simplification of an earlier model with John, Paul, and Carlos, a student from IMPA that all of us worked with him. So you see the wave sort of sloshing, as I call it, goes back and forth, back and forth, back and forth, and generates this harmonic-like oscillation. And on the sides, there's basically nothing. It's quiescent to the fluid. So later on, in a second, this is one cavity, one droplet. Later on, I'll do several cavities and two droplets. And we'll see actually two droplets at a distance interacting. So this is just so we get the picture that I always show you, which is the evolution in time in a cavity. Here's very quickly, I'm not going to get into details of the equations. It's basically just a generic view of the equations. In this paper of the tunneling, I'll talk a little about what tunneling. There's details about this model and references to the even more complex model than this one. The two equations.
We cannot hear you.
Yeah, Andre, your audio is cut. I might try without the headphones. Can you do that? I think shutting down Zoom would probably be a good idea.
Now can you hear me?
Or shutting down, yeah.
It's strange. It's going a little crazy. Sorry.
It's okay.
Oh, sorry. I hope it hangs in here. So the two equations on the top left are the equations for the position of the droplet, x1, x2. Eta is the wave elevation on the right, which the slope, that's how it guides the particle. And below are the wave equations that we couple to this model, which allows the droplet to make waves through these two pressure terms, PD, that you see on the bottom. I'm not going to get into further detail of the model, and of the gravity is a time varying gravity. So the dynamics is done in the reference frame of the vessel, the fluid vessel. So these are the system that we have for the particles coupled to the wave. So if anybody has questions later on, I'll be happy to answer and actually share the papers with the modeling. Let's go to simulations. So there was this very nice paper by the Paris group on the unpredictable tunneling. So with this 1D model, we were able to do tunneling. So I can do 2 cavities using some math tricks for bottom topography, which is something I have some previous experience. And here's the first interesting thing I think I would like to share with you. Notice on the side, this zoom on the droplet on the right cavity, making an attempt to tunnel to the cavity next to it with a high barrier, and it does not succeed. Later on, it does succeed. And the first thing that called my attention a long time ago is that actually the activity in the empty but neighboring cavity prevented the droplet from tunneling. And this is very recurrent. So the dynamics in the neighboring cavity, even when it's empty, is important. On the right, we see this long simulation with the tunneling. And indeed, we see it is, as seen in the lab, no surprise, unpredictable in many ways. You cannot predict when it's going to tunnel, and you cannot predict the time of residence. But as Mathieu mentioned in his talk 2 days ago, it's 50-50% the way in this scenario it can be in each cavity. Okay, so this was a wonderful HQA meeting organized by Giuseppe in Calabria 2015, just actually before I went to the wonderful visit to MIT. And I was actually tuning things for our tunneling paper, and this is what I noticed. Let me show you that again, the side cavity, empty cavity, plays a role. So there's already some non-local effect. And as I was mentioning before the coming into the talk, I make a distinction in my way of saying things between local, meaning point-wise as a particle is, non-local, which is due to the pilot wave, the dressing of the particle, which has a compact support, which depends on memory, and global. So we see that things are not really global, but as I changed a little bit the barrier height in the middle, separating the cavities, look at the difference of the dynamics of the droplet on the right cavity because of the activity in the empty left cavity. So this is very important. I mean, this sort of non-local forcing at a distance. Having seen this numerically, this in showing the Calabria thing, during my visit at MIT, I revisited some of this in the recent paper. This is the reference to last year. So in my visit to MIT, at the very end of the visit, Miles Couchman was very kind to do some experiments where he actually imitating the numerics. He had an empty cavity in the middle, 2 droplets. Here you can see the 2 droplets oscillating. Let me turn it on, going in and out, in and out, in and out. Miles did the FFT for the dynamics of droplet 2 on the right. And you see this blue curve here on the bottom where you see the main frequency and the secondary harmonic, which is a signature of the forcing at a distance, not even from the neighboring cavity, from the one far away. And then when droplet 1 coalesced, disappeared, it's the red curve. So you see a slight frequency shift in the oscillation, and the secondary harmonic, that is the forcing at a distance, disappears. So this was a communication we did with John and Miles at the APS meeting just after I left MIT. Okay, having all this in mind, then I'm going to start doing 2 droplets now in the numerics and see if I can push them far away and see if they actually have a correlated dynamics. Okay, so the first simulation is basically 2 droplets in the same cavity. So these red and black traces are the position of the droplets. It's not actually the size of the droplet, it's a small cavity. I put the droplets, you see at the bottom, in an asymmetric position, one more towards the right and the other one not so close to the boundary, and I let them go. The wave-mediated dynamics, right, as John mentioned, how people, this dynamic potential on the background, which is the wave, guides the 2 droplets to a symmetric position. I on purpose did not put them in a symmetric position, and they start oscillating. And it looked like here, looking at this, that they're oscillating like you saw in the experiment, in and out. So in the next slide, I'm going to do this. Since they're going in and out, I'm going to reflect one of them so I can see if they're moving together, doing exactly the same thing. So I'm reflecting the black trace to the direction of the red one. And now I'm going to look at this in phase space so I can see cycles. I want to see cycles so we can see things doing cycles instead of just going like this. So I position and speed. So I already halted the animation where these spikes is exactly when the droplet feels the wave and then it flies. Feels the wave and then it flies. So when it feels the wave, it's surfing the wave, it gets accelerated. So you see these red and blue traces, the particles adjusting themselves on their own spontaneously due to the underlying wave dynamics. And they start doing this limit cycle, one in blue and one in red. And it was remarkable that after a while, as you will see just in a second, they migrate to a common limit cycle and basically synchronize spontaneously. Like now, something happens and they go to another limit cycle a little bit in the middle, and let me make this run fast, and there's the limit cycle, and that is spontaneous due to the underlying wave field. Okay, so I said, wow, this reminds me of the famous model by Kuramoto, which has the model for spontaneous synchronization of nonlinear oscillators. So this is a phenomenological model for phase transition that Kuramoto did in 75. And it's a limit cycle model in the sense it does not care about the amplitude of the cycles, it cares only about phase. So it's a phase dynamics. He was able to devise one model, simplified model from Winfrey that allowed one to do mathematics. Still, they're like open theorems related to this problem, where the sign coupling is the nonlinear thing, and the coupling matrix can be a coupling constant in some cases, which means all oscillators in this population are coupled in the same way. And usually the theorems are good for large populations of oscillators. And in terms of large population of oscillators, tomorrow you will see a very nice videos and presentation on this subject by Pedro Sanz in the work with John and collaborators. So Kuramoto showed that depending on the coupling, you can get phase locking, which is what you see in the bottom right, partial phase locking, and incoherence. And the centroid sort of indicates in what regime you are. But this is basically a model only for the phase. With a droplet, we're going to look at, we're looking in phase space. When I look in phase space, I see the radius of the cycles or the cycles, whatever, and the angle dynamics both together. So let's go to another simulation. I'm going to start putting now my droplets further away. So I'm going to put the cavity in the middle, and and in calibrating this, as Mathieu pointed out, the mid cavity plays an important role in being deeper. It strengthens the coupling between the two droplets. And because it's basically locally, the Faraday threshold is lower there. So it sort of amplifies the signal, the wave, the little ripples that are trafficking in the domain. So here I have the droplets 7 Faraday wavelengths apart. That's already more than seen in the laboratory by both the French and MIT group in a paper where they show that droplets can interact and fall into orbits if they're like 3 or 4 Faraday wavelengths away. Here it's 7. Okay, and then I'm going to reflect and let me show you what happens. You know, here you look at the oscillations. They're not so nice. Are they doing something similar? Well, they're going to both droplets are going to migrate to this complicated sort of sequence of cycles. I call this maybe a reference orbit. Maybe it's a stable orbit because these guys are following the same sort of trace. Oh, this is a projection of phase space in 2 dimensions, so I can see both of them because I have now 2 particles. And look at the animation on the bottom. The diamond on the left basically indicates I'm doing the average of the position. So if the diamond stays still, the droplets are synchronizing. Okay, so they don't synchronize all the time, but they synchronize quite frequently. So now look, the diamond is still, and you can see them zipping, just the position of the droplets zipping over this sort of spiral-like orbits, but they do the same kind of cycle, even being far away, each one trapped to its cavity. So through the tunneling simulations, I kind of learned how to trap. When I mean trap, is have a very, very low probability of the droplets escaping, but still allowing the waves to sort of ripples to fall to overcome the barriers and generate some sort of communication among the droplets. That's the main idea. So here we see this very complicated, so differently from the Kuramoto one, we can see that actually the amplitude of the cycles is changing, and both droplets change accordingly at a distance of several wavelengths. Okay, so I went happily after seeing this to try to break my record, okay, for droplets far apart. Oh, before, let me show you how minor differences change things. This is a recent one from this fluids paper I showed you. I changed the cavity size a little bit, as you see up on top, and I had more difficulty of finding synchronization than in the other one, which was the cavities of 1 centimeter. Another important thing, I played with the depth of the mid cavity. Here in the bottom, the animation on the left has a cavity of depth 2, and the one on the right, cavity of depth 3. In the cavity of depth 3, it synchronizes more often. And as you can see, the only changing the mid cavity, which is basically the communication cavity that establishes this sort of transmission line between the two guys, the two droplets, changes the dynamic entirely. So there's really a non-local effect, in my language, non-local, not necessarily meaning global, effect of the dynamics by this wave underlying Faraday wave field. Okay, so now I think I'm going to go to the slide where I try to break my record, putting the droplets far apart. But here you can see that minor changes in the cavity, which in some sense is minor changes in the potential of the particles and also the potential that sort of establishes the communication, changes the dynamics quite a bit. Okay, so these are two reference papers that I mentioned. One is this, the walk-in droplets correlated, which I'm going to show you actually, I think, the most important result of the top paper, the chaos paper, in the next slide. So here it is. So here I got frustrated for a few days when I did this simulation, because I wanted to see Kuramoto-like synchronization with the droplets set far apart, now 13 wavelengths apart, almost 100 droplet diameters apart. Okay, I had to put two cavities in the middle for numerical reasons, or else because the code is linear, or else it would go Faraday unstable. So I put two cavities instead of one to separate the droplets. A huge barrier, quite wide barrier, and you can see this. Look at the waves. If you go above the barrier, you can see that the wave trace is quite faint, meaning that the communication was almost not established. But the fact that I have the two deep cavities in between in this communication transmission line, and since it's closer to the Faraday threshold in the mid cavities because it's deeper, it sort of amplifies the signal and establishes some communication, as I will convince you, between the two droplets. But then why was I frustrated? Because when I looked at the black trace and the red trace, it doesn't look like it's synchronized. It doesn't look like it's quite doing the same thing. And I said, oh my God, I lost the very nice Kuramoto-like synchronization I had seen in the two previous examples. So I said, well, let me look at this, do the animation for this in phase space, doing the reflection and so on, to see what the droplets are doing, if I can see something. And things were still quite complicated. So this is sort of the underlying orbit, the reference orbit that both droplets do. So, and there's going to be zipping around this. Let me turn on the animation. Off they go, and they never synchronize. The droplets actually never get close to each other. And I mean, John and some of you have heard me mention this a few times. My intuition was a little bit like two motorcycle guys racing on a track, trying to get each other, accelerating, decelerating. So the phase is highly nonlinear. It accelerates, decelerates, accelerates again, turns around. They never get close to each other, but they're doing the same track. These racers, right? They're doing the same track. And the figure on the bottom, I removed the contact time so we don't see the spikes. We see a slightly smoother orbit. And then I asked myself, what do these two guys have in common? What do these two droplets have in common? I sort of lost the coherence, the synchronization of the Kuramoto model, the spontaneous synchronization, the spontaneous coherence, right? Phase transition to a coherent state of the two droplets. So after a few days looking at this, I said, well, in quantum mechanics, always have quantum mechanics on the back of our minds, even though this to me is already interesting in the sense of nonlinear dynamics of coupled oscillators, I said, well, let me look in phase space. Where are these guys more likely to be found? Right? They're accelerating, decelerating, accelerating. So where are these guys more likely to be found? Particle 1 and particle 2. So I did a binning. I did a mesh in phase space in 2D, a 2D binning, and I do a histogram to see a little bit like a numerical probability distribution to see where I can find these guys. And after 5 days of frustration of looking at this, I had a great pleasure, jumped out of my chair when I saw this. The two droplets in a statistical sense are identical. So I decided to call this statistical coherence or statistical indistinguishability. Because if I look at only the statistics of these two droplets, they're the same. It happened to be a bimodal situation. There are other situations where it's more like it has a preferred spot, like this yellow spot. And actually, if you look at how these histograms are built, if I do them in time, they're not symmetric. Sometimes one part builds quicker than the other, but if you wait long enough, this is what you see, and these guys look pretty much the same. Now, if I remove one of them, so I see, are they really talking to each other? So I repeat the exact same simulation, and I remove one of the droplets, and here is the histogram for the single droplet. So the phase space dynamics has to be described when there's the two droplets by the system as a whole. It cannot be by each particle independently. So in principle, this dynamics is not separable. Okay, now ongoing work to finish the last maybe 4 slides. This part, Mathieu did a very nice presentation. I'm going to talk very quickly about this. So it's basically the one that we did, the metastability. So on the left, you see tunneling with 50-50%. Now, if we calibrate, as you've seen, the mid cavity properly and so on, you get a 2-level cavities, which you get this metastability, where the 2 levels of energy of the 2 cavities, you have this quick visit and it comes back. Then, as Mathieu showed out, you have this collective behavior, which is the probability of the droplet tunneling might be enhanced or diminished by playing with the length, the width of the mid cavity, and therefore with analogies to super or subradiance. And here you see other simulations that actually I was doing on my own also to get intuition. Here without one droplet, there's just very rare tunneling events. With 2 droplets, you have this middle one with the same shaking strength. And actually, if I increase just a little bit the shaking strength, you get a slightly more, maybe one more tunneling event for both guys. And actually, this histogram here on the bottom shows that in the middle one, for example, the time of residence, even though they tunnel at different times, but the number of tunneling is more or less the same, the time of residence and the PDFs for them are pretty much look the same, even though it was not tunneling at the same time. Okay, but Mathieu already showed this in a very nice way, very nice presentation. The other ongoing work is with John, as John mentioned, also with Nathan Kutz at Washington and Peter Badu at MIT. We're all looking at this. Is we went back to a single cavity. And in a single cavity, this actually has to do with questions that were asked in terms of, even though we have dissipation, we have viscosity, and we have forcing, can we have some sort of, starting from Navier-Stokes, which is how our model starts, can we have some sort of energy balance? Well, look, depending on how I set things, how I set my cavity, I can actually have a model where the droplet, I put it at the side of the cavity, and it spirals in phase space to the center. And this is due to the wave sloshing that stops, and it goes to a bouncing regime. Well, but this doesn't have to be the same. Depending on how I calibrate things, I get basically one that actually, it goes to a limit cycle. There's an orbit, there's an attractor. This is calibrating the cavity size and also how much you shake and so on. It's a very fine tuning. So here in the bottom is a graph that I'm going to show, another one where I have the droplet in the beginning over this cavity and the wave that guides it in time. And with Nathan, one thing that we're attempting to do is, Nathan is an expert and has codes for this, which is a dynamic mode decomposition, which allows you to do a model discovery. So as I mentioned right in the beginning of my talk, in some cases, it looks like a harmonic oscillator. So to get a leading order harmonic oscillator for this limit cycle is not that difficult. but to get more sophisticated models where you have sort of a effective energy conservation like dynamics. Here it happens that we have a balance between dissipation and the forcing, and it's almost like we have an effective Hamiltonian to some extent. So this study with Nathan, we're looking into finding model discoveries, and who knows, maybe a model discovery in the future that here we have the forcing the balance that actually leads to a similar histogram that we find here, and who knows, maybe even a Schrödinger type model that it's probabilistic dynamics, if we want to call it, leads to the same one of this full, more complicated model. So that's something we're looking at. And finally, my last slide is is this. This is the wave sloshing, this thing. And how about the average wave field? Something that John pointed out, average wave field that looks like this underlying potential, something that rings, I was almost going to say rings a bell, but I know it's not good to maybe say rings a bell for many reasons. Well, but connects to things that, that have been talked here. So using a very nice result by Dury, Milevsky, and Wang, they basically have a formula where they show that this integral here of putting together the probability measure mu integrated against the bouncing a bouncer at fixed points gives you exactly the average wave field of the dynamics. So you can connect something that's probabilistic, right, the invariant measure here, to an average wave field. So I did this for, this was actually a suggestion by John, I did this for this model, right? Here is basically, I had to force my bouncer to stay at a point. So here, this graph is very nice because you see in the white part of this figure, you see the bouncer generating its wave field. It sort of oscillates a little bit, then it stabilizes. Once it stabilizes, I get the very end trace and say, okay, this is the function that represents the bouncer at that point. And when I do this and I compare, so here there's a ghost indication of the histogram. When I compare that with the average wave field, which is just averaging over 1,000 Faraday periods, which is the blue curve, and I use this formula from Dury and collaborators, actually using just half of the grid points. I only used half the grid points to save time. It's right on the money. So you actually see that how the connection between the average wave field and the probability distribution mu in this very nice formula in this paper by Dury and collaborators, which is a follow-up on another paper by Matt Dury with John, which actually is in a periodic domain and so on. And this one, so there's a convolution. This one appears in this projection way. Basically, you project to some extent the bouncer on your histogram, and that gives you your average wave field. So I think I've gone basically almost over all my time. Here are three of the relevant references for this talk. Of course, there's references within these papers, review papers by John in our previous papers. And once again, thank you very much, Paulo, for the invitation, for being here, this very nice meeting. And thank you very much for your attention.